Hello, calculus students. Today we're going to be doing an introduction to Taylor polynomials. So I'm going to share my screen and start the presentation. Okay, we'll start this. So it says that we are going to be learning how to construct a Taylor polynomial from scratch. Well, why do we need a Taylor polynomial? A Taylor polynomial, let me grab my pen here. And you can just add this to your notes. A Taylor polynomial is a way to use a polynomial to approximate some other curve. Ooh, crazy pen. And it'll say we're using it to approximate other functions. All right, so in this example, we have the cosine curve, and it says find the equation line tangent to y equals cosine x at x equals 0. So I want to find the equation of the tangent line here. Well, it would be hitting at this point. And most of you can see the slope is 0. It's a horizontal line passing through 1. So the equation of the tangent line should be y equals 1. You could go ahead and go through, find the derivative, approximate it at the point 0, 1, etc. This is the equation you'd come up with. All right, so this is y equals 1. And then it says, notice our approximation has the same y value as the slope of the original function. What other property could be used so that it matches that point? Well, the other thing we could look at this point is the second derivative. We could talk about some concavity in here. And it says, what degree polynomial would this approximation be? And if we were talking about the concavity, that would be degree 2, because it would be the second derivative. All right, let's look at our next slide. So we are now going to do this approximation. I'm going to grab a different color. And so to write a quadratic approximation of a function, well, a quadratic expression usually looks like something squared plus something times x plus a constant. We're going to write it actually in reverse order. And you'll see why this makes sense in a bit. So I have my constant term, I have my x term, and I have my squared term. And for the function we are approximating, we're using this to approximate f of x equals cosine x. That's what we had on the first slide, our first example. All right, so if I take the derivative of this constant will go away. Derivative of bx is b, and the derivative of cx squared would be 2cx. If I take the derivative of the function we're approximating, the derivative of cosine is negative sine x. Next, we take the second derivative. Again, this is a constant, that's going to go away. The derivative of 2cx would be 2c. And our second derivative here would be, and that's a second derivative, doesn't really look like it there, would be negative cosine x. All right, when it talks about the center of approximation, that's talking about the point where we were doing all this approximation. If you recall, this was at the point x equals 0. So we can look at approximations at different places on the curve, but in this example, we, excuse me, we're using 0. So now we're going to go through that process we just did, but we're now in place of x, we're going to be substituting x equals 0. So f of 0 would be a in this case, because if I substitute a 0 in here, it goes away and that goes away. So in terms of, and I can go ahead and write that down so you can see what we're doing. Okay, we're just left with a. In terms of the function we are approximating, f of 0 would be cosine of 0. And the cosine of 0 is 1. All right, for this one, the second one, If I substitute 0 in for x in my second derivative, I'm going to be left with b. In this case, if I substitute 0 in for the second derivative, or excuse me, the first derivative here, f prime of 0 would be negative sine of 0, which is 0. Okay, now we're on the second derivative. If I substitute 0 in here, there's nowhere to substitute 0, so we have 2c. Right? We don't have any x's anymore. On here on our second derivative, we have the second derivative of 0 would be negative cosine of 0, which would be equal to a negative 1. All right, then it says use the table above to find values for a, b, and c. Well, in this case, we have our a. I'm going to switch colors here a second. I'll switch back to my red. All right, if we look, we have a is 1. Our b value is 0. And our c value, we have 2c equals negative 1. I'll just write that off to the side here. 2c equals negative 1. So our c value would be negative 1/2. So I'm going to use those values to find a quadratic approximation for cosine x, and it would be 1 minus 1/2 x squared. All right, again, this is our constant term. We don't have an x term. This is our x squared term. And then it says, sketch your approximation in the graph above. If we go back to the first slide, or you guys can do this on your notes, obviously this is a sad little parabola. It's centered at 0, so you can add this to your graph on the first slide or on your paper. This time it says, use the same procedure to write a 6-degree Taylor polynomial for cosine. So we just did a quadratic, and now it's asking us to do a 6-degree. So grab my pen. So if I have a 6-degree, I'm going to have a plus bx plus cx squared plus dx cubed plus ex to the 4th plus fx to the 5th plus gx to the 6th. All right, the function again that we are approximating is y equals cosine x. Right. So first derivative, any term that we have that contains a constant is going to go away. So this term goes away. I now have derivative of bx would be b, derivative of cx squared would be 2cx, and so forth. So I'm just going to keep going along here. You guys could even pause the video and write this down yourself and then keep simplifying. All right, derivative of cosine is negative sine. All right, derivative of b would be 0. Derivative of 2cx is 2c, so I keep going, using the general power rule here to simplify. All right, derivative of negative sine is negative cosine. Derivative of 2c, C is a constant, so that goes away. So we now have 6D plus 24EX. And remember, those letters like E and F and so forth are just constants. It's just a way to write the notation. And my pen is going haywire here. We should make smooth letters. X cubed. All right. We're now on the third derivative, which would be sine x. All right, back to this, 6D goes away. We have 24E plus 120 fx plus 360 gx squared. And hopefully you guys can read those. That's a squared. All right. When we write fourth derivative, you may or may not remember this. We don't make all the little hash marks. We just put a 4 in parentheses. Derivative of sine is cosine. All right. 24e, it's a constant, that goes away. We're left with 120f here plus 720 gx, derivative, fifth derivative of our original function. Derivative of cosine is negative sine. And that's a 5, by the way. All right. And last, we end up with 720g. Okay, hopefully you've caught up with all of that. And then y to the 6th is equal to cosine x. Ooh, negative sine is negative cos. Okay, let's look at our next slide. Okay, this time we are going to be using our polynomial and finding our different values. So you can look back at what you had above. F of 0, I grab my pen. F of 0 would just be left with our a, because all the other terms in our polynomial contain x. For the function we're approximating, that would be our cosine of 0 is 1. So our a is 1. All right, for the second one, and you guys can do this, f prime of 0 would have been b. For our function, f of b, or f prime of 0, would be negative sine of 0, which is 0. So our b value is 0. Okay, for our c function, remember our second derivative was 2c. So second derivative at 0 of our cosine function, when we get down to that one was negative 1, if you remember, because it's negative cosine. We have already solved this one before, so we have c equals negative 1/2. So far these are all ones we've done before in the previous steps. Now we're down to the third derivative, and that was 6d. In our third derivative of our cosine function, we were down to sine of x, so sine of 0 is 0, and our d value here is equal to 0. Our next one, we have 24e. Our fourth derivative of our original cosine function. When we get down to the fourth derivative, we are back to cosine of x. Cosine of 0 is 1. So our e value here, 24e equals 1, so e equals 1/24. Our fifth derivative, we had 120f, right? This is just putting in 0 for all those x's we had. the fifth derivative of our original function would have been negative sine 0, which is 0. So our f is equal to 0. And lastly, we have our 720g was our last step in our original polynomial. Our sixth derivative of 0, that's a 0, would be negative cosine x is negative 1. If we solve that, our g is equal to negative 1 over 720. All right, so now it says, write a sixth-degree Taylor polynomial approximation for cosine of x centered at 0, also known as a Maclaurin polynomial of degree 6. So when you have it centered at 0, a Taylor polynomial turns into a Maclaurin polynomial. And these are both named after mathematicians. You can read about them in your calc book. So we are going to write this, and this is how we write it. This is our approximation for a Taylor polynomial. We do this p subscripted x. We're using it to approximate cosine x. So I'm going to write all that we have in here. So I'm going to put these variables in here and substitute it in to figure out our cosine function. So this would turn into 1. Okay, the next one we have is our, and remember, this is our degree 2, right? So we have negative 1/2 x squared. All right, we skip our cube step. We're now down to the 4th power. So we have plus 1/24 x to the 4th. Okay, this is degree 5. This is degree 6. So minus 1 over 720 x to the 6th. Right. Another way to write this, and you may or may not notice, but I'll go ahead and tell you because it's going to be what we use for our approximations. This is the same thing as 1 over minus x squared over, and 2 is the same thing as 2 times 1, which is 2 factorial. This term is x to the 4th over 24, which I can write as 4 times 3 times 2 times 1, otherwise known as 4 factorial. And our last term is x to the 6th over 720, which you probably have guessed is 6 factorial. All right, so that's no surprise that that does that. That's the way these are going to look when we do our approximations. All right, let's look at our last slide. The question is asked, can you find, or I really should say, what is the 8th approximation, right? If I do an 8th degree, it would turn into just what we had. So if I'm using this to approximate cosine again, cosine of x would be equal to, or approximately equal to, this time we have an 8th degree approximation. So it would have been our 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And if we're doing an 8th degree approximation, it's going to be plus x to the 8th over 8 factorial. Right? It asks, why is this important? Because it's a lot easier to find derivatives of polynomial functions and integrals of polynomials and so forth if they're centered at some value like 0. And it's just easier to work with polynomials than it is to a lot of other functions. All right, I'm going to go back a slide here because one of the things it said to do was to graph your result. So that polynomial we had, the 1 minus 1/2 x squared plus 1/24 x to the 4th minus 720 x to the 6th. If you type that into your calculator and also type in your cosine function, you can see how closely that our polynomial really does approximate. It's pretty cool. So that's it. You guys are now free to do the next section, which is doing the notes for 10-6 and the 10-6 assignment. So good luck. Email me if you have any questions, or you can ask me in class.